In our last part of the course here, we're going to talk about what are called normal curves. And we're going to use these curves to answer some questions regarding probability. This is something that those of you who ever go on and take a statistics course will do quite a bit. You'll study normal functions and use them to find areas under a curve. And by doing so, you can answer all kinds of questions about probabilities. The only things I expect you to know about normal curves are that the mean of the distribution tells you where the center of the curve is. Whatever kind of curve you have, whether it's one that's skinnier or spread out a little bit more, you always have the mean in the center. The mean determines where the middle of your graph is. Another thing that's important is that the standard deviation tells you how far spread apart the graph is. So if you have a small standard deviation in comparison with the mean, then you end up with a skinnier looking graph. If you have a standard deviation that is larger in comparison with the mean, then it's going to look a little bit more spread out. Another thing that's good to know is that the area under the curve is 1. The total area under the curve is 1. And you don't need to worry right now how this works. It's beyond the scope of this course to actually calculate the areas by hand. That would involve calculus, which we're not getting into in this course. But you find probabilities by finding areas. That's what I want you to understand. You find probabilities by finding areas under a curve. Okay. So to do that, to make it possible to look at a normal curve for every possible situation, we're going to use what are called z-scores. Now, there would be infinitely many possible curves because for every different mean and standard deviation, you would have a different curve. But what we can do, we can basically translate all of those infinitely many possible curves to just one particular curve by using what we call z-scores to standardize the graphs so that there's only one curve necessary to study. To calculate a z-score for a data value, you use this formula. You take the data value minus the average, and you take that result and divide by the standard deviation of your data set. Z-scores tell you how many standard deviations a value is above or below the mean. So if you have a data value that has a z-score of 0, well, you're right on the mean. If you have a data value with a z-score of positive 2, that means you're 2 standard deviations above the mean. If you have a z-score of negative 3, that means you're 3 standard deviations below the mean, and so on. So 0 is the z-score for the mean. Positive z-scores are above the mean. Negative z-scores are below the mean. People will use z-scores in statistics a lot. One thing they do is they use z-scores to figure out if data values are outliers. Just an approximate rule of thumb is that a data value with a z-score above 2 or below negative 2 is considered to be pretty unusual because 95% of your data values are generally going to have z-scores somewhere between negative 2 and 2. And if you have a z-score above 2 or below negative 2, that means it's really unlikely. There's about a 2.5% chance of that happening. The farther a z-score is from 0, like a z-score of 3 or 4, those are more and more and more unusual, very, very unlikely. Now, one thing that's cool about z-scores is you can use them to compare data values from different sets to see which one is more unusual for its particular set. For example, in sports, you can use z-scores to compare individual performances from completely different eras. And we're going to do an example of that right here. It says, in 1927, the average number of home runs for the top 10 leaders was 28.5 with a standard deviation of 13.6. That year, Babe Ruth set a record with 60 home runs. So let's calculate the z-score for Babe Ruth. To do that and calculate his z-score, we take his data value, which was 60. We subtract the average, which was 28.5, and we divide that by the standard deviation of 13.6. I'll usually round z-scores off to about 2 decimal places here. So 60 minus 28.5 divided by 13.6. We end up with about 2.32. So Babe Ruth had a pretty unusually high number of home runs, more than 2 standard deviations above the average. Now let's compare that with the current record number of home runs in a season, Barry Bonds in 2001. In that year, the average number of home runs was 52.6 with a standard deviation of 9.1, and Barry Bonds hit a record number of 70 home runs. So let's calculate how unusual that was in comparison to his peers at the time. To do that, we take his value of 70 minus the average of 52.6, and we divide that by the standard deviation of 9.1. And let's see, 70 minus 52.6 divided by 9.1. We end up with about 1.91. Still very high. Still, almost 2 standard deviations above the average of the top 10 hitters. So that's still extremely unusually high. But in comparison to their peers at the time, Ruth was more unusual because he had a higher z-score. The higher your z-score, the more unusual you are in comparison to the other data values in your set. Or in the case of low scores, it could be the lower the z-score, the more unusual it is. All right, so something I was referring to a little while ago is that we're going to use these curves to find the probability of being in between 2 numbers. Here's in general how it works. Let's say we have a curve like this. And suppose we have a value over here of A and a value right here of B. If we wanted to find the probability that our variable is in between those numbers, what we would do is calculate the area under the curve in between those numbers. And by calculating the area, we're able to find the probability of being in between those numbers. Now, as I was saying earlier, to calculate that area mathematically, you have to use calculus, which we're not going to do. But we are going to use one of the calculator's functions to do that for us. On the TI-84 calculator, if you press Math, and then press the right arrow key 3 times to get to the PRB menu. And then what you want to do is you want to scroll downward until it's a slightly different entry on different versions of the calculator. Oh, wait. Oh, this is very embarrassing. I did that wrong. I was thinking of something different. But hey, I'll fix it. Okay. I was looking at the completely wrong calculator function there. What you do is you press the second button and then the button that says VARS. And then the second one is what we call the Normalcdf function. And what you do to find the probability of being in between 2 numbers, when you enter that on your calculator, it's going to look like this. Then you would put whatever your lowest value is. So in the case of this example right here, we would put A. Then you put your highest value, which is B, and then you put the mean, and then you put the standard deviation. All of those with commas in between. The comma on the calculator, by the way, is right above the 7. If you look at the number 7 on the calculator, there's a comma key right above the 7. This can all seem really confusing until we actually get into an example, and you'll see how it works. Here it says, Dixie Office Supplies find that its sales force drives an average of 1,200 miles per month per person with a standard deviation of 150 miles. Assume that the number of miles driven by a salesperson is closely approximated by normal distribution. And part A says, find the probability that a salesperson drives between 1,200 and 1,600 miles per month. So to do that, we're going to use that Normalcdf function. So we press second, and then the VARS key, and 2 for Normalcdf. Whoops. Now, some versions of the calculator, it takes you to a screen where you just enter the lower number, the upper number, the mean, and then the standard deviation. Some versions of the calculator, it actually types up this expression. The versions of the calculator are slightly different. But in this case, we would put 1,200 for the lower number, 1,600 for the upper number. Our mean, we're given right here, is 1,200. And then our standard deviation we're given right here is 150. Make sure you figure out where the Normalcdf function is on your calculator and that you learn how to use it to do these sort of calculations. Let me take a second here and enter it in my calculator. And I end up just rounded off to about 4 decimal places. We get about 0.4962, just rounded to 4 decimal places. Suppose we have the same thing, but it says, find the probability that a salesperson drives between 1,000 and 1,500 miles per month. So we're going to go to that Normalcdf function again. This time our lower value is 1,000. Our upper value is 1,500. We still have the same mean and standard deviation of 1,200 and 150. I put that in my calculator and I end up getting 0.8860, just rounded to 4 decimal places. And that's it. Now let's take a look at the next one. It says, find the probability that a salesperson drives less than 1,350 miles. So we're still going to start the same way. Press second, VARS, and 2 to get to the Normalcdf function. The trick is when you have a less than problem, that means there is no smallest number. So basically, you want to enter something really small. I usually just do something like -1 million. And then here, I want my highest possible number would be 1,350. My mean is still the same of 1,200. My standard deviation is still 150. And when I put that in, whoops. Oh, I typed it in wrong. I made a typing error on my calculator. There, now I've got it fixed. Here I end up getting about 0.8413. Now, if we have a greater than, or as it says here, a more than problem, in this case, you put that number you want to be more than for your lowest possible number. Here we want to be more than 1350. Now, when it's a more than problem, that means there is no highest possible number, so I put something big, usually something like 1,000,000. So I'll put, let's see, second VARS 2. I'll put 1350 for my lower number, 1,000,000. For my upper number, my mean is still 1200. My standard deviation is still 150. And here I get about 0.1587 for the answer. So it's going to be very important that you learn how to use this Normalcdf function on your calculator. That will make it a whole lot easier to answer these sorts of questions.